Welcome, I'm Mr. B. This tutorial is about thermal expansion in materials. We are going to try to utilize this equation for the expansion of materials. A little background about myself. I hold a bachelor's of engineering degree, and in my lifetime I've also worked construction field jobs such as painting homes in new construction and existing residential homes. I'm going to use an example of what I've seen in a lot of homes, cracked drywall, and try to use this equation to validate a reason why I think drywall often can crack. So if you like my content, please like and subscribe. I hope to put some more out there here in the future, but let's look into thermal expansion of materials and try to do some calculations. To start off, what is thermal expansion? Well, if you think about hot air, any kind of fluid, as you warm it up, it expands. It's easy to see with a balloon. If you were to take this warm balloon, you could maybe put it into a refrigerator or freezer, and a little while later come back and find that it has shrunk in size, right? Pretty easy to think about that concept. But what's happened with a solid? So a solid has a lattice structure, and the same thing can kind of happen. It's just harder to imagine and see because it's very tiny in the atomic structure. Because when you look down on an atom, electrons, they're actually in shells, orbitals. These are called orbitals surrounding the nucleus here. And this is just hydrogen. So as energy is added, which think of energy being heat added to a material, the electron can actually come out to a further orbital or shell. As it loses the energy to cool off, it shrinks back down to a smaller size or the smaller orbital. So that's what's happening on an atomic level. Let's look at what can happen here then. So with materials, you may see buckling happening. An example here is roadway. It gets really hot in the summer, things expand, and next thing you know, it pops up and cracks. On a bridge, they place these here finger-laced type metal connections that allow for the bridge and the roadway to expand and contract without buckling and breaking. Because if a bridge broke or buckled, that could be extremely bad, right? With piping, you may see some kind of rubber connection that allows it to move. And in a rail line, this is an old-time photo, but it was quite an issue a long time ago where the heat of the day, that railway would buckle. Imagine the force it would take to shift a rail line like that. Quite a lot. There's also contraction. When things cool off, they shrink, they get smaller, and then cracks occur. You see it in roadways here. Here's some cracks that are visible. Concrete, you can find cracks. And drywall, like I was talking about before. This is a garage where you have a crack across the ceiling in the corners. Let's talk about these garages here. Underneath the drywall is some trusses here, framed out with wood, and often a crack will form all the way down the center. So on this here garage, if they had drywall up after a bunch of years, I would often see a crack forming all the way perpendicular to these trusses, all the way down, right in the center here. So let's try to use the equation to see if we can calculate out some length changes and determine if temperature change is maybe causing cracks in drywall. This is the equation that we start with. But what are these components? Well, so on top here we have triangle L. That is delta L. It's called delta, this symbol, L. Think of it small to large, large to small. It's the change in length. So we start with our length final minus our length original, or 0 or not. So we call this length not in mathematical terms. Think of it being the starting stage, its original length to start with. We're taking our length final minus our length not. Same thing over here with our temperature change, delta T, our temperature final minus our temperature not, or temperature original to start. And here we have the Greek letter alpha. This is the coefficient of thermal expansion of the material that you're using, that you're calculating with. But where do we find this value here? Because you can think about lengths, you can measure like your original length, and you can get temperatures easily, right? But where do we find coefficient of thermal expansion? Well, websites like the engineeringtoolbox.com, or I used roofonline.com to find some building materials. There, you may find a whole list of different materials, and they can give you values to use in millimeters, or I'm sorry, meters and degrees Celsius, or inches and degrees Fahrenheit. So we have some options here: perpendicular to the grain, or wood with a fir. This is a species of wood, fir. Wood parallel to grain, or wood as in pine. Pine is another species of wood. Parallel would be, think about going a long way to the grain. Perpendicular is across the grain. Gypsum board is just the name for drywall. It's a type of compound that drywall is made of, gypsum. And here's the value for that. So if we took a truss, we are going to look at the length across this bottom, which is called the bottom chord. Many garages are 24 feet long or deep. So if you pulled your car in, you probably have some space in the back to put some small items, or a cabinetry, or shelves, or toolboxes. A lot of times I see garages are basically 24 feet long. I live in Wisconsin. We are going to use some temperatures here. I'm not going to choose 114 degrees, a max high, record high. Instead, I'm going to choose 110. If you think about up in that attic of the garage there, and up in the high part of the ceiling, it's hotter. So if the temperature outside, I've been out there with 100-degree days, it could easily be 110 inside that attic there, where it's heating up from the outside sun on the roof, or up in that ceiling area. So I'm using 110 for my high temperature. My low temperature winter, I'm just going to choose 0 degrees F. Typical temperature, I love walking around when it's 65 degrees Fahrenheit. I'm just going to use that as my temperature, not my temperature, my starting temperature. So we have our formula to start with that we saw before. And now we start to find some data to start plugging into those parts. I found the coefficients for my materials here. The gypsum board is 8 times 10 to the negative 6. And as for my wood choice, I'm going to go with the parallel to the grain. Wood parallel to the grain. 1.67 is the inches and Fahrenheit measurement here. 1.67, that's 10 times to the negative 6, that value there, okay? So I have my original equation, but how do I find what I need? How do I plug those in? Okay, because I actually think I should look for my length final after I increase or decrease the temperature. So let's see what we can do here with our delta L, delta T. We're going to plug these values in, and now I've expanded this equation to show what's happening over here on the length side. Our length final minus our length not, our original, over length not equals the coefficient times our temperature final minus our temperature not. Next, I'm going to multiply the length not, bring it over to this side. You can see I just brought it over. Then I'm going to add the length original to this side. I just tacked on to the back here, right at the end. So this is the equation I want to use to find my length final after I increase or decrease the temperature. So back to some of our information we had. Our length original was 24 feet. I've now converted it. 12 inches over a foot becomes 288 inches. Our temperature original, our temperature not, I'm using 65 degrees Fahrenheit, a nice walking around day. Temperature final for summer, 110 degrees Fahrenheit. And temperature final winter, 0 degrees Fahrenheit. My coefficient for the wood, I am using 1.67 times 10 to the negative 6, and my gypsum or drywall is 8 times 10 to the negative 6. I'm going to use these values and put them into this formula to find my length final. We started out with our length final here formula. I started putting values in for the wood. This is summertime, so summertime temperature. Okay, you're going to subtract these here to start in parentheses. It's a positive value, right? Multiply that by this really tiny number because it's 10 to the negative 6, very, very small, and multiply that by our length original, 288. This whole number in these parentheses, it can be very, very tiny. It's added on to our original, and you see it's only going up 0.022 inches. Okay, so you add some heat, and the wood has expanded barely any bit at all. If you look in winter, now we have 0 degrees minus our temperature not, which is 65. Now our value is negative, okay? And this is going to be a negative number, negative 60 minus 65. Multiply that by our 1.67 times 10 to the negative 6 and our 288 original length. This is going to be a very small number, and it's negative. So it's going to subtract from the 288. See, it got smaller. Think about when things get colder, this value should get smaller. When you're doing these calculations, if it gets warmer, think about increasing, it should get longer. When it's getting cooler or the temperature is dropping, you are going to see a smaller number, it'll shrink. But that's not very much, right? The difference, 0.052, barely anything. I would have thought wood would expand further, especially in a long distance. It's very surprising to me. So wood has 3 directions, or everything has 3 directions, okay? And in this case, we chose the long board length, okay? The longitudinal length, parallel with the grain. So we chose a 1.67, and if you look here, another option was perpendicular to the grain. That would be radial or tangential. And in that direction, it expands 16.7, which is 10 times more than the long way. So as a board heats up, it actually gets fatter in the radial and tangential direction compared to the longitudinal long direction of the fibers. It gets fatter 10 times more than the length. Okay? So the drywall. Let's do some calculations here. You start out with our original calculation, our equation. Start plugging in some numbers. We're doing the summertime, and it's 110 degrees Fahrenheit, minus 65 to start. We have that 8 times 10 to the negative 6, multiplied by our length of 288, add it to our length. We can see that's increased 0.104, quite a bit more than the wood did there. In wintertime, now remember, it's shrinking, so we have our 0 degrees Fahrenheit minus 65, multiply that by our coefficient and our original length, add it to our length, and you can see it's shrunk. Total difference, 0.25, a quarter of an inch. So you have that garage ceiling drywall over the top of wood. Each of them are moving differently. The drywall could be moving in that amount of length, quarter of an inch overall from cold to hot. That much difference it's moving around. Whereas the wood is not moving as much. Could this be why then a crack forms? They're joined together with screws and nails, and if they're joined together and one is moving more than the other, that could cause a force to happen, such as a crack. The crack then is going to take place where there's a seam right along the middle of the drywall, and that's commonly what I see in almost every garage I go into here in Wisconsin. So what are some fixes? Well, honestly, just put some caulk in there. The caulk, if you use a high quality caulk that can expand and contract with temperature change, be flexible, you paint over the top of it, at least you won't see that dark seam of a crack. And you'll see this kind of stuff on roadways. They put these caulk strips and tar down. The bridge we saw before, they put this joint in there that could then move, allow the bridge part and the road to now have some ability to expand and contract without buckling and cracking. And then like a railway, they might put a joint in also, so you can expand and contract without having buckling happening. What about pipes? Well, this is called a relief section. So now, instead of a straight pipe going all the way through, you give it the ability to actually expand and contract and move and flex in this curved area here. Okay, that gives it the ability to have some relief in that piece. Then you can also drive under them. So in this section, they might have it set up so it has some relief there. It's a shorter distance here compared to if this was all one long pipe across. You can see another example over here. And you could do a rubber type expansion joint that covers over the connection to allow for movement. Well, that's thermal expansion materials, my explanation of it. I hope it kind of showed you a real world explanation of how cracks occur, such as drywall in your garage, in your home. And I hope from it you've now seen how to use the equation that brings about the length change, temperature change, using the coefficient of that material. I hope you like my stuff here. If you do, please like and subscribe, as I hope to bring out more content weekly. Thanks for joining me. Have a great day.